Okay, so so again, good morning to you all. So today is the third and last lecture of, or at least the formal lecture of this series. We keep on talking outside the classroom, of course. The first two lectures, we looked at the historical development of standard model, and the last lecture was focused on foundations of standard model like gauge symmetries and electroweak symmetry breaking. Today, we will spend discussing the flavor structure of standard model, because that forms a whole field of its own. As we know, there are dedicated experiments, especially to probe the structure of flavor in the standard model. Okay, so that's what we will try to look at today, right? Because till now, whatever we had done yesterday in the gauge symmetries and electroweak symmetry breaking, as long as you have one family, everything was the same. But now we have three families, first, second, and third, or three generations. Gauge structure is identical. However, we know that at least if we focus on the quarks, the masses are quite different. As we go to higher and higher generations, the masses of quarks keep on increasing. Also, we know that the quark family is mixed. We will look at that in detail. And mixing is rather strong within the same family. U and D have, well, not mixing, but strong coupling, but across the families, it becomes smaller and smaller. Okay, so that's the general principles. Okay. I just want to give you a glimpse of what the study of flavor structure has told us in the development of standard model. So these things, some of them we actually talked about when we, in the first lecture, when we looked at discoveries of particles. So let me point you out some things which actually were discovered because the people tried to study the flavor structure in some sense. So one of the first ones is the so-called tau theta puzzle. I will come to that. It was a puzzle when two particles that seem to have the same mass and the same lifetime decayed to different final states. One particle decayed to 2 pions, second decayed to 3 pions. Okay? That was the puzzle that actually led us to suspect that there is parity violation. And now we know that both the tau and theta particles were the same as charge kaons. Okay? So these are not the tau that we call currently. So the tau as was named in the, I think, 40s. Then Cabibbo came up with the idea of the Cabibbo angle of quark mixing, and that told us that it is possible that the interactions that we see with all the mesons, as well as with the decay of muon, for example, are governed by the same weak coupling. So there is a weak coupling universality, and plus there is some kind of quark mix. We mentioned the GIM mechanism or GIM mechanism sometime. It was observed that KL to pi does not happen. So there is no flavor changing neutral current at the tree level, and that led them to propose that there should be a charm quark for which there was no experimental signature at that point of time. Next part, which we'll discuss quite extensively today, is the paradigm of Cabibbo, Kobayashi, Masukawa. The CKM paradigm indicated that there should be at least 3 quark families, and no, this was also done before the third family actually was discovered. Then people observed a large BB bar mixing, and as it turns out, the amount of BB bar mixing is governed by the square of the top mass in the amplitude, and therefore observation of large BB bar mixing actually led us to well, it indicated that a top quark indeed is heavy, okay? And that was something that was so through the calculation of a box diagram. And then the rate of radioactive B decay was found to be quite high, but once you measured that, then again that is connected to the square of top quark mass through the so-called penguin diagram, and the estimation, I would say prediction of top quark mass also came from the rate of radioactive beta. So some of you may not know of these things, but this was just to give an indication to say that standard model that flavor physics has played a major role in developing a standard model coming to the stage that we are in. For those who are new to this, this is a language I'll be using. There'll be, of course, pions and kaons, which everybody knows. All charm mesons will be called as D. about 1.5 to 1.8 GeV. All the bottom mesons will be called as B, and the quarkonia will be referred to as phi, j psi, and epsilon. Is strange, charmed, and bottom. Okay, so these particles are going to appear all the time in this. So this is a slide worth in getting introduced to. Okay. So this is what we'll do. We'll make some short comments about discrete symmetry of standard model. Remember, the gauge symmetry was a continuous symmetry. So alpha of x was a continuous parameter. So of course, standard model also has some discrete symmetries. We'll talk about them. We'll talk about how to measure CP violation in the decays of particles and in mixing. We'll also come to what mixing is. As I promised you already, we discussed the CKM paradigm in detail and look at flavor tests of the CKM paradigm. We will not dwell too much into flavor in lepton sector because there are 2 lectures on neutrinos happening in the next week. So we'll go there only if there is time, and then we'll take. Okay, so let's start with discrete symmetries of standard model. Okay. And I try to divide them into 3 parts. Okay, so one is what I call accidental symmetries. So as we know, standard model seems to conserve leptons and baryons. However, there is no principle in standard model that tells you that they should be conserved. Gauge symmetries have nothing to say about lepton or baryon violation. In fact, we know that there are solutions to the standard model field equations which do violate the value of B plus L. Okay, so standard model as a gauge group conserves B minus L, but does not conserve B plus L. Okay, let's not go into that because we know that whatever we see in the colliders, at least baryon and lepton numbers seem to be conserved independently. Yesterday, we talked about Majorana neutrinos. Okay. The fact that Majorana neutrinos are allowed in standard model comes from the fact that standard model does not really worry hard and fast about lepton baryon violation as long as B minus L is conserved. There are some symmetries which are discrete, which we know are broken. Okay. So we know, for example, that parity symmetry is broken, charge conjugation symmetry is broken, time reversal symmetry is broken, and the CP symmetry, which is often called charge parity, which is actually charge conjugation parity, is also broken. Okay. And we will spend a lot of today's time discussing about the charge parity symmetry, but we'll also perhaps go through some part of parity symmetry. And as far as we know, there is still one unbroken symmetry, which is CPT, and the CPT is conserved. In fact, as long as we trust the standard model is a local quantum field theory, CPT is going to be conserved. Okay, so at least that is beyond doubt, unless you want to construct some new theories. Okay, so we'll start with violation of parity. So as I mentioned earlier, there was this tau theta puzzles where 2 particles with the same mass and lifetime seem to decay to pi and 2 pions and 3 pions. A 2 pion final state has parity +1, a 3 pion final state has parity -1. Okay. So since people believed that parity is conserved, it was thought that these 2 particles are different. And that puzzle state for some time till people accepted that this was the same particle that decayed to both 2 pions final state and 3 pions final state. And as I mentioned before, that turned out to be a charge chaos. So Li and Yang in 1956 proposed the possibility that parity is broken, which essentially means that if you do an experiment here and look at the same experiment in a mirror, you film them separately, give them to some independent observer, the observer should be able to say whether this was film taken in real life or film taken in the mirror world. Okay, that's the layman's way of saying this. We of course have more concrete ways of saying what this exactly means. So experiments were done immediately following this suggestion in 1957 by Madame Wu and by Friedman Telegdi. And Gobindo informed me yesterday, although I did not check, that these actually were published in the same PRA one after the other. Yeah? So So Badamud experiment was the famed cobalt experiment, which is often there in textbooks. So you have a cobalt nucleus. You look at cobalt 60, look at it decaying, and you observe that more number of beta rays go in the direction opposite to the direction of spin of the cobalt nucleus. Okay. The experiment of Friedman-Telegdi was the one where I think it was the Brookhaven, there was a pion beam, they stopped pion beam, pion decayed to muons and muon decayed to electrons. They looked at the angular distribution of these electrons and it was not isotropic. That indicates that there is some parity violation. So almost immediately the next year, Li and Yang got the Nobel Prize for this. Around the same time, well, a few years later, Nicolas Cabibbo observed that the coupling constants of muon decay, neutron decay, and kaon decay seem to be very, very similar, and they could be related like this. So I must say that this is a reconstruction of what he would have thought, because the measurements were not as accurate at that point of time, and it was not possible that he would be able to check this. Okay, it was consistent, is all I can say. Okay. However, his proposal was that indeed all of these three decays are governed by the same coupling constant, and that same coupling constant G is just what you can call a G of muon decay, where muon goes to electron, and then U quark must be coupling to only one combination of D and S. Remember, D and S have the same charge, -1/3, so they can mix into a quark called D prime, and this is the combination to which U quark couples. Therefore, when the U quark and D quark are coupling, this decay is proportional to GUD, which is cos theta, and when U and S need to couple, this coupling is proportional to GUS, which is sin theta. Okay. So this was the first indication of flavor mixing, consistent with the data at that point of time, but of course more data made it more and more clear. So now we call this angle theta C as the Cabibbo angle, and we know its the size of Cabibbo angle is about 0.2, so that's a good number to have in mind. Okay. So this was the GI mechanism that we talked about earlier. Okay. So this Cabibbo angle tries to relate decays that involve U quarks and D quarks, and one might see that these two decays seem to be related by simply replacement of a U quark with a D quark. Okay. So with some other caveats, one might expect that the decay rates might be very, very similar, but they happen to be different by, I think, more than 8 orders of magnitude. In fact, during that time, KL2 mu mu was not even found. Do we have a measurement of KL2 mu mu even now? No, right? Yeah. So it is so low that we do not even have a measurement of KL2 mu mu even now. So the suggestion was that perhaps there is another quark called as C quark, or the charm quark. Now this charm quark couples to the orthogonal combination as D prime. Okay. So D prime, if you remembered, was cos times D plus sin times S, and here the C quark couples to minus sin times D plus cosine times S. As a result, what happens is, in addition to the process where S goes to D through a U quark, it can also go to D through a C quark. Okay. And now if you calculate both the amplitudes, they add up and they cancel. Okay. As a result, this process, which is a flavor changing S to D, neutral current, because both have the same charge, is actually highly suppressed. Okay. And this mechanism was called as the Jim mechanism, which proposed existence of charm quark. Okay. So that's one more feather in the cap of flavor physics. So now we know that we have pairs of quarks. We know that parity symmetry is broken. People don't like breaking of symmetries. Okay, so you always find some hope that we'll understand something which will stay symmetric. So one of the major reasons why parity was seemed to be broken was, for example, that neutrinos happen to be only left chiral. Okay. So we had left chiral neutrinos, but we did not have right chiral neutrinos, and that's a very big breaking of parity symmetry. On the other hand, we had right chiral anti-neutrino. Okay? So we had, so this means it looked like if you change parity as well as charge, into charge conjugation, things perhaps were symmetric. Okay? So it was suspected that maybe you break parity, maybe you break charge conjugation, but you combine two of them and the symmetry will stay a symmetry. Okay? This is a nice picture made by one of my old friends, Tobias Hurth. So this is a painting of Escher called Day and Night. So parity symmetry is essentially taking reflection in this mirror. Charge to conjugation symmetry is going from here to here when you change black to white. And then you see whether you apply P and CP again, whether you get to the same figure or not. And Tobias's observation was that with the original painting of Escher, there is actually some difference. And he always claimed that this was the cause of charge parity violation. Okay, that's a joke anyway, but it's just a nice thing to have mixing of art with science. The way to test whether charge parity is conserved or not was first obtained from the decay of K mesons. Now, neutral K mesons, of course, have a K0 and a K0 bar, right? So K0 is ds bar, K0 bar is SD bar. Now, the decaying eigenstates, if CP is conserved, would be the same as CP eigenstates, which would be K plus K bar and K minus K bar. Root 2 is, of course, normalization. This is CP1, this is CP odd. Now, because we assume parity is conserved, CP1, K1 will decay only to pi pi, and CP odd will decay only to 3 pounds. Now, decay to 2 pounds is easier. Therefore, this is short-lived, called K short. Decay to 3 pounds is more difficult because you have less amount of phase space. And therefore, this particle is long-lived, and we call this as K long. Okay? In fact, the ratio of the lifetimes is of the order of 600 or so, 600 to 800. I forget exact number. Okay? So this is really, really long-lived. So originally you produce a K0, and that is a combination of K short and K long. So what do you observe if there is charge parity conservation, and what do you observe if there is charge parity violation? So this was the experiment of Cronin and Fitch in 1964. If charge parity CP was conserved, you would find that this green particle, which is your K short, will decay to 2 pions, and K long will decay to 3 pions. Okay? So if you go very far away from the starting point, you will only get 3 pions. Okay? However, there is some possibility that the K short or the CP even, CP or K long actually oscillated back into K short because there are K bar oscillations. And because of the oscillations, if you go far away, there will actually be some component of CP even already present, which will decay into pi pi. So this will be called CP violation through mixing, because this violation occurred because K1 and K2 mix amongst each other. The third possibility, which you see is quite different from this possibility, was that the violation was not because K short went to K long, but because CP was violated in the decay itself. So all the way that you see here, this is still a K long, but the K long is now decaying to 2 pions. So this part was called as indirect CP violation. This was called as direct CP violation. What you observe is a combination of the two, and indeed it is a cleverness of the experimentalists that actually managed to separate these two parts out and figure out which is the contributions of both of them. In fact, it turns out that both of these do contribute. I will show you, give an indication of how to look at that mathematically, okay, in just a bit. But this experiment confirmed that the hope that CP combined will be a conserved symmetry also turned out to be false, and we know that CP is violated. So it raised many questions, and answer to these questions actually took almost 30 more years to get a definitive answer to this. And the reason for that is just the experiments to check this were very difficult and had to be constructed. So one question was, is CP violation small or large? In the K1 system, it was observed to be of the order of 10 power minus 3. So one would say it is very, very small, very, very naively. Now we know that it is of the order of 1. Okay, so it is actually very large, but for that we have to look at decays of B mesons. So question was, is CP an approximate symmetry? We now know that it is not, because violation of CP is not 0.1%, it is of the order of 1. Is the symmetry breaking spontaneous? Yesterday we saw a spontaneous symmetry breaking of electroweak symmetry, of the gauge symmetries. It could be that way. However, as we will see today, we have a very successful mechanism called a CKM mechanism, which tells us that the symmetry breaking is not spontaneous symmetry breaking. It is a symmetry breaking that appears in the Lagrangian itself. Okay? We will see Lagrangian for CP violation today. Okay? And then the question is, where does it come from? Whether extra interactions? So from the discovery in 1964, it took almost till 2000 to be sure that there was that other candidates were ruled out. You might have heard of things like super weak interactions and so on, which was a very very popular model when I was a graduate student. But once data came, all those models fell to the wayside. And as we will see, the CKM model actually emerged as the right one. Okay? Yeah. So how do we measure the CP violation? What are the detectors we use and what are the processes that we use? So these are some of the first two experiments, NA48 and KTEV. KTEV is the one where actually I worked during my first 2 years of graduate school. I worked on trying to develop the cesium crystal calorimeter and the TRD for some time. Yeah, which I think Daniel mentioned yesterday about. So I was one of the first ones to polish the cesium crystals that came to Chicago. And I tried to do some experiments on getting TRDs. We also tried to make straw detectors with proportional chambers with straw detectors. I think Bruce Winstein and Nick Solemi and Yao Hua were working on this. So this is my experience with instrumentation. It mainly goes on KTEV. Unfortunately, I was not there when KTEV actually started. I had already left for my postdoc. Then, of course, these are B physics detectors, Babar and Bell, which were the first two so-called B factories, which focused on producing lots of B mesons and analyzing them. And they gave us lots of important results. Currently, we have the Bell 2 detector running in Japan. There are people in TIFR who work on this. And I also met some of our colleagues here. I think there are people here, right? Who work on Bell 2. Yeah, I think people from it's a Ljubljana group, right? I met them yesterday who were on Bell 2. So anyway, yeah. So this is of course another working B physics detector that we have. LHCb is of course a dedicated experiment to look at B physics at LHC. So this is the LHCb detector. And CMS, although it's not built for detecting B mesons, a lot of B physics can also be done with this. I'm sorry I don't have an atlas figure, but no, since but since we have CMS colleagues, I thought I should also show a CMS figure. A lot of measurements from CMS and atlas also have been instrumental in telling us things about B physics. I will show you some of them. But this figure, I guess everybody has seen, and if you haven't, you should see it and try to understand every detail of this. It's a wonderful figure. Whoever thought of making this figure is a genius. Okay. Thanks for getting it. Okay. So there are certain things that you need to see if you are doing B physics. Okay, just a few small things. One is, the nice thing about B mesons is that they have a reasonably large lifetime, that if they are formed at a vertex, they can actually travel a bit before decay. And as a result, if this is the primary vertex, a B meson produced will travel a short distance and then decay. Identification of the fact that there is a secondary vertex which is away from the primary vertex is one good indication that this was a B meson traveling. Okay, so the secondary vertex is one good thing to have. Second indication of identifying a B core is that the jet which is formed by B core is slightly wider, okay, than the jet formed by lighter jets, and you will sometimes hear the word called as fat jet when you read in papers or in articles. Another language that we will often use while talking about decays of B mesons is the so-called B tagging. Now, this comes because of the following. As we saw, K and K bar mix amongst each other. Similarly, B and B bar also mix amongst each other. Okay, so they form a pair, they form an entangled pair. And as a result, at one time, you cannot confidently say whether one particle is a B or a B bar, okay, because they are interacting with each other and you are not sure which is what. However, if one of the particle decays, I think this is the right one, and you can identify that this decaying particle was a B0, you will know for sure that the second particle which came paired with this was a B0 bar at this time. Okay. So, for example, this particle B0 has decayed to a D0 bar and a pi minus, K plus, pi minus, and a mu plus. Okay. The fact that you get a mu plus is a strong indication that you have to start from B0. You could try drawing Feynman diagrams. You will see that a B0 will always give a mu plus, whereas a B0 bar will give a mu minus. Okay. So once you have a positively charged muon, you know that this particle was a B0. So you mark the time at which this particle decayed. So this tells you that at this time T1, this particle was a B0 and this particle was a B0 bar. Now from this B0 bar, you can proceed, you see when this B0 bar decays, and since you know how the mixing of B0 bar occurs, you know that when it decayed at time T2, what was the superposition of B and B bar that this particle was in. It's a very interesting quantum mechanical problem to do, something that involves superposition, entanglement, all these buzzwords that we hear today in quantum computing. We have been, of course, doing this for more than 20 years, I'm sure. Yeah. So this process is called as B tagging, because this means that you know what fraction of this is a B and what fraction is B bar, although at the time of production, you were not aware of this. Okay. What are the processes that you want to see if you want to study CP violation? You want to look at those processes for which the amplitude of initial state X to final state Y is not the same as amplitude for the antiparticle decay. So X bar to Y bar. Of course, we can't measure amplitudes, we measure decays, we measure decay rates. So we don't measure this, but we actually measure the square of this. So what that means is if these two quantities differed simply by one complex phase, it doesn't matter, right? So square of this will be the square of this, and therefore this CP violation, if it was different by only a phase, will not be an observable object. If you want to observe CP violation, what you need is not a simple amplitude like this, but a process that goes through an intermediate step. So the same process, X to Y, suppose it happens through two intermediate states. Once through some particle called W, and next to some particle called Z. Okay, these are just particle states, not the standard W and Z particles. These are just, this may be even 2 or 3 different particles. Okay, the amplitude of X to Y then becomes this. Amplitude of X bar to Y bar then becomes this. Okay. And now if you try to square up this amplitude, then you realize that these don't have to be the same. Okay. Because even though these two can be related by some phase, and these can be related by some phase, when you add them and square them, you will get an interference term. An interference term doesn't get cancelled out because of the phase. So it's very important to get interference term, and which means that you have to get a complex amplitude. This will have some phase, weak phase phi1. Here, this should have weak phase phi2. This phi1 and phi2 should be different, in which case you will be able to observe CP violation. So observation of CP violation needs some thing which is complex between these two amplitudes, and therefore couplings which have to be complex. So that's the final lesson. We'll come to that when we talk about the mechanism of Kobayashi and Mascara. Okay, lesson from here is that you need complex couplings if you need observable CP violation. Okay? And any example of processes that you will see, you will notice that indeed there is some complex coupling present somewhere when people measure CP violation. Okay. I promise you that I will indicate to you the method by which you actually make this measurement, the quantities that we actually end up measuring. Some of the very interesting quantities which can be measured in CP violation actually come from the mixing of neutral mesons. Very similar to what we talked about kaons earlier. We had K and K bar. They can mix amongst each other and decay to 2 pions and 3 pions. Okay. This is a B and B bar. For example, I have taken a BS0 and BS0 bar. They can mix between each other. This is a standard box diagram that shows you that they are allowed to mix. Okay. As a result, now we have the usual quantum system in which two objects mix amongst each other. If you want to write the Schrodinger equation, H cross is 1, of course. You write R d by dt of this state, which consists of B0 and B0 bar. This is B0 and B0 bar. This is the effective Hamiltonian. And this Hamiltonian will have a part which is called the dispersive part, which is M, that's Hermitian. And this part corresponds to the decay, and this is also called as the absorptive part. Okay. So this Hamiltonian now is a non-Hermitian Hamiltonian, but both M and gamma are Hermitian matrices, and these are their components: M11, M12, M21, M22, and so on. This is a convention that we'll use in the next slide, and that's the reason I want to tell you what these objects are. With this, now it's a sort of standard graduate school problem. You find eigenvalues of this matrix, you find eigenvectors of the matrix, and then you see how things evolve. Okay. Once you find eigenvalues of the matrix, which are M and gamma, you'll be able to find the mass difference between these two states, which is delta M, and you'll be able to find lifetime difference between those two states, which is called a delta gamma. Okay. So measurements of delta M and delta gamma are an important part of determining the CP violation. Okay. The eigenvalue equations, which can determine the value of delta M and delta gamma, can be written in terms of M12s and gamma 12s. You will see here that only M12 and gamma 12s appear in this, whereas M11, M22 just disappear. Gamma 11, gamma 22 are not dependent on this. Okay, so it's very important that delta M and delta gamma simply depend on the quantities which are off-diagonal elements of this matrix. And you will notice that off-diagonal elements simply mean the matrix, the elements that couple B0 to B0 bar. Okay. So B0, B0 bar mixing is a very important part of getting mass differences and lifetime differences. Okay. You can write down the decay rate of initial B going to final state F as a function of time. Because remember, as a function of time, B will keep on going to B bar will keep on going back to A, back to B. Okay. So do not be scared by all these stain symbols. What I'll show you what you need to see. The first line here is normalization. So simply forget about this. This just gives you factor of e power minus gamma t, which is the decaying part. Next line is important. In the time dependence, you actually get 4 terms. One depends on cosine delta mt, one depends on sine delta mt, one depends on cosine hyperbolic of delta gamma t, and one depends on sine hyperbolic or delta gamma t. All of these have coefficients in front of them, and these coefficients are essentially your measurables. So the coefficient of cosine delta mt is called as ACP direct. The coefficient of sine delta mt is called as ACP mixing, and the coefficient of sine h delta gamma t is called as A delta gamma. These three are the measures of CP violation. So in an experiment which discusses mixing of objects, these three quantities are to be measured. Now these three quantities are written in terms of, again, just one quantity, one complex number called as lambda f, and lambda f is simply the ratio of the amplitudes with some multiply constant. Okay? But again, you will see, if you really want to see CP violation, this lambda f has to be imaginary if you want to see CP violation in mixing. And if you want to see CP violation in a direct CP violation, the value of lambda f should have magnitude which is not the same as 1. Okay. So all of these measurements finally lead you to measurement of one quantity called lambda f, assuming the decay is simple. Okay, decays are not always as simple as that, but that's something that one has to keep in. Okay, so now what we know from all this is that CP violation will involve somewhere complex amplitudes and therefore complex couplings, and we know what to measure from this. Okay, so now we come to how standard model tries to explain CP violation in terms of its flavor structure. Okay, so these two guys were the ones that actually said this. It's now more than 50 years that this mechanism has come, and as we will see, it has survived so far. So this is Kobayashi-san and Masukawa-san, who were the ones who wrote this paper of CP violation in the renormalizable theory of weak interactions. A few of you asked me yesterday or day before about how did we know that the SU2 weak gauge theory should couple U and D and C and S. Okay. And I just repeat the answer for the benefit of everybody. The answer is we did not know. People tried out many different combinations of trying which to form in doublets, which could form triplets, and so on. And in fact, this paper, 80% of the paper is about this. It says what would happen if U and D form a doublet? What would happen if UDS form a triplet? What would happen if you consider DS as a doublet and U as a singlet? So this paper essentially is about that, trying to figure out what kind of gauge symmetry actually would work. And finally, I think in one short paragraph, they say that, but this is all with 2 generations. But suppose we had 3 generations, we won't have to do all these things and we'll get our answer in a very simple. Okay, so that one paragraph plus one matrix actually did give them the Nobel Prize in 2008, I think, if I'm correct. Anyway, so let's go to the argument, simply because if you haven't seen it, it's a very beautiful argument. Okay? The first argument showed that if you have only 2 generations, you cannot see CP violation. Okay? So what happens? If there are 2 generations, then your Lagrangian will basically be, if you want to write down the charge current interaction, which means interaction between UC on one hand, which are charged 2/3, with DS on the other hand, which are charged -1/3. So this has to be combined, these two have to be related with a most general unitary matrix, which has one angle and 3 phases, phi1, phi2, and phi3. So trust me that this is the most general 2x2 unitary matrix that you can write down. But now, remember, we have no idea about the phases of these quantities, and those really don't matter. So we can take globally that each of them, we just redefine their phases a bit. Instead of DL, we multiply DL by e to the power I phi1, SL by some I phi2, and CL by this combination. And we'll notice that now this is our new DL, new SL, new UL, and new CL, and then the mixing is simply a real matrix of cos, sine, and cos. So this tells you that in principle, there is no coupling constant, effective coupling constant that is complex. We can always take away all the parts that are not observable, and what remains is simply a real quantity, and therefore this will not give you a CP violation. So this is explicitly seeing this, but there is a nice argument which deals with counting of numbers. Okay, counting is interesting. So the idea is, if we have a 2 by 2 complex matrix, which like this matrix that you saw here, this matrix typically has 4 elements, okay? All 4 are complex. So 4 real plus 4 imaginary quantities. Okay? Now we put a condition that this matrix has to be unitary. So which is U dagger U is equal to identity. These are 4 conditions, 3 of which are real, 1 is imaginary. So if you use these conditions, you are left with 1 real quantity and 3 imaginary quantities. And now, as we did earlier, you have 4 quarks, U, D, C, and S. You take one of the phases as a standard phase and choose the 3 relative phases between these quarks. Choose them such that you get rid of those 3 phases that you had. As a result, the mixing matrix is completely real. Okay? That's exactly what we saw in the earlier slide. So this tells you that if you have a 2 by 2 unitary matrix, then you can always convert it to a matrix which is completely real, and so therefore you will not observe CP violation. Okay. Now you go to 3 generations and do the same kind of counting again. Okay. So 3 by 3 matrix has 9 real and 9 imaginary quantities, okay, because 9 complex numbers from 3 by 3 matrices. Condition of unitarity gives you 6 real conditions and 3 imaginary conditions. I mean, conditions on the imaginary part of this equation. So you are left with 3 real parameters and 6 imaginary parameters. Okay. But now, earlier you could have 3 relative phases because you had 4 quarks. Now you have 6 quarks, so you have 5 relative phases. Okay. You remove those 5 phases, okay, but you are still left with 1 imaginary quantity. Okay. So which is to say that if you are going to have a 3 by 3 unitary matrix, even if you choose your quark phases in a very clever way, you will not be able to get rid of 1 phase. So the most general matrix of this kind always will have 1 complex parameter, and the Kobayashi-Masukawa suggestion was that that 1 complex parameter is the reason for CP violation in the standard model. Okay. So they claim that you need 3 families for this complex nature. This is our modern way of looking at it. They did not write in this language, but that's the language that we write things in. So we say that U prime is our flavor basis, right? Which are UCT and DSB as our 3 flavors of quarks, 2 pairs of triplets of quarks, okay, 2 triplets. The charge current interaction that you write simply tells you that you have a U-type quark, which is this, D-type quarks, which is this, and they are coupled using a W with gamma mu, as we saw yesterday. So all you have to do is, instead of writing things in the flavor basis, which is U prime and D prime, you write them in the mass basis. And for mass basis, you have to rotate by some unitary angle, unitary matrix. So this DL prime becomes V times DL, where V is unitary. And this UL prime becomes UL times V dagger, where V is unitary. So this new Lagrangian now, you see, has a mass eigenstate UL bar, mass eigenstate D, but now these 2 matrices, which are unitary, get multiplied together to give you another matrix, which is also unitary, because if you multiply unitary by unitary, you get unitary matrix. And this matrix is what we call as the CK matrix. So the claim was that a simple change of basis from flavor eigenstates to mass eigenstates of up and down type quarks actually gives you a matrix which necessarily has a complex component. Okay. And the claim is that this complex component will tell us about all CP violations. Okay, sorry. I will do, all right. So nice thing about unitary matrices is that you can form many relations. No? U dagger U is equal to identity actually consists of 9 different relations. Okay? One of the most celebrated relations is actually this. Just one second. I just want to, yeah, sorry, I had to go one step back. Okay? So this VCK matrix is written like this, where VUD simply means that it's a coupling between U and D quark, and the coupling constant is proportional to VUD times the original coupling constant. The values of these have been measured, okay, and depending on the hierarchy of these values, Wolfenstein actually came up with a nice parameterization of this matrix in terms of 4 parameters, which were lambda, which are the Kabimo angle, then A, which is here, then eta and rho, which exemplify the complex nature of this particular matrix. Okay. So eta is the only quantity in this, as you see, which comes multiplied with I. So whichever quantity has eta will display a CP violation. Okay. If eta by rho is large, it means the CP violation is large. Okay. And one nice property of a unitarity triangle is that you can always form one combination that does not depend on how you determine the phases of quarks, how you define the phases of quarks. This quantity is called as Yaskov invariant, and this quantity turns out to be equal to a square lambda to the power 6 times eta. Okay. Indeed, it turns out that all the CP violation that you see in standard model is always proportional to Yaskov invariant. Okay. And that's again a nice thing to see by actually doing calculations. Yeah. So unitary matrices have some nice relations. For example, you can have a relation like this. No, VUD, VUB star plus VCD, VCB star plus VTD, VTB star equal to 0. Okay. This relation, again, somebody who thought of it as a genius, you can look at it as a complex number plus second complex number plus third complex number giving you 0, which means that these 3 complex numbers form a triangle. Okay. And now if you look at this triangle, you will find that with proper normalization, this base, if you normalize it to 1, a third vertex is just rho comma eta. I have said rho bar comma eta bar. There is some small correction to that, which I will not go into because we are short of time. But that's essentially very similar to rho and eta multiplying by a constant, which is just 0.98 or something. Okay. So this is a triangle. People try to measure the sides and angles of this triangle because this triangle is in some sense the proof of CK paradigm. And what do I mean by that? The angles of this triangle are what are called as alpha, beta, or gamma. Or if you are on Bell, you'll prefer calling them as phi 1, phi 2, and phi 3. But I'll stick to alpha, beta, and gamma. They are easier to say. Although I know there are Bell people in the audience and not Babar, but I will take that risk. Okay. So these are very well defined quantities. Okay. Do not depend on what kind of phases that you use. So this was just one triangle, but UU dagger equal to 1 actually has 6 such relations, and there are 6 such triangles. In principle, trying to construct each of these triangles would give you a different test of CP violation. But as we will see, just one triangle is enough to tell us a lot about what we can measure. This is the most explored triangle. The reason is because all 3 sides of this triangle are approximately of similar order of magnitude, so it is easier to measure. These other triangles are actually somewhat flat triangles, and therefore the errors make things hard to measure. So for example, if you look at this triangle, this side is about 10 power minus 3 times this side. Okay, and such triangles are always very, very hard to construct. Okay, so we know that there is only one phase that controls CP violation, so only one Jansky invariant, and therefore we are going to try to reconstruct this triangle in many ways. Okay. So this triangle, we'll draw it in the plane of rho and eta, because we saw that the vertex of this triangle is actually rho and eta. Okay. Okay, since time is short, I will very quickly show you some of the major measurements that have tried to find the vertex of this triangle. So remember, if you try multiple experiments and find the vertex of the triangle, and all the experiments converge on one single vertex, that tells you that what you thought of is correct. If there is something missing, it's possible that if you do many measurements, you will not be able to get a consistent solution. So I'll show you the flavor test of the CKM paradigm done in different ways, and what are the constraints that seem to be on the vertex of this triangle. Okay. I will show some expressions, not tell you exactly how they come from, but the pictures are going to be what is going to tell us something nice. So for example, you look at semi-leptonic B decays. Okay. If you look at these two, everything else is very well known, and you can calculate VUB over VCB, and that turns out to be rho square plus eta square. So in the rho eta plane, this will be like a circle. Right? So in the rho eta plane, semi-leptonic decays give you constraint that looks like a circle. Let's not go to details of this because time is short, but you can look at decays of B going to D mesons, and D mesons further go to K plus K minus. Okay. If you make these measurements, details again we will skip, you measure the value of sine of gamma. Okay, so remember, gamma was one of the angles of the triangle, the angle at the center. So this measurement gives you the error on gamma as in this band. Okay. So of course, this band will always overlap with this circle, so that's not a surprise. Okay. But at least it's good that we have been able to measure this angle of the triangle. You go one step ahead, try to look at our KK bar mixing. Remember, we found measured CP violation in KK bar system many years ago. This gives you again a combination of rho and eta, which you see as this, I guess this is slightly pink band, and it also goes through the intersection point of the earlier two bands. Okay, so that's nice. You can do the same thing with BB bar mixing with the B0, B0 bar, and that will give you this semicircular part that you see, slightly more than a semicircle. Okay. Again, the overlapping part actually stays, so that's good for us. You make measurements of BS bar system and find out the value of delta M in the BS bar system, and that again is consistent with the values that you have got. Okay. So we are getting more and more consistent with what we had. You can measure value of alpha from the decays of B to pi and K. This actually was part of my PhD thesis. This alpha is these gray kind of bands, and again very nicely passed through this. And then we come to one of the most accurate measurements of CP violation measured, which is the angle beta. And again, this angle beta will give you this green triangular region. And as you see, all of them very precisely seem to overlap in this very small region. And that vertex will tell you the value of rho and eta. Okay. If you want to be very precise, rho bar and eta bar. So this tells us that multiple experiments that we have done have given us the same value of rho and eta. Okay. Now definitely this is not a coincidence. So we know that at least to leading order, CK matrix is able to explain all the measurements that we have that involve the value of that involves some kind of CP violation. Okay, so this is just to show you quickly how things build up. Okay, but finally you have. Okay, so till now we observed no deviation from CPM predictions, and therefore have constrained many physics models. Okay, so I'm going to skip flavor in lepton sector. Maybe I just show you this once, which is one of the interesting things about lepton sector is measuring exactly the width of Z. Has told us that there are exactly 3 light neutrinos, and therefore exactly 3 generations. You look at this number, it is 2.984 plus minus 0.008. So we know this error to an accuracy of better than 1%. The point actually lies right on top of what we will get if you had 3 neutrinos here, and you'll see this is right on top. All the curves match with this. Definitely 2 and 4 are ruled out. I won't talk about neutrinos much because Albert Gago will give lectures on this next week. Okay. So my concluding remarks, okay, because we talked about landscape of standard model. 3 days are grossly insufficient to be able to cover this. The question is, of course, is the landscape complete? Of course, there are some important parameters that are still unknown. We need to measure them correctly, especially in the leptonic sector. Although we know how QCD functions, QCD calculations are very hard, and therefore making predictions is difficult, especially making predictions that have non-perturbative quantities. So, of course, it's not completely understood. Is it all there is? Again, we know that it is not. There are certain things that we know standard model does not resolve. We don't have an answer for what is dark matter and dark energy. We do not know where the matter-antimatter asymmetry comes from, how the Barron asymmetry is produced. We have CP variation in the standard model in the quark sector, but we know that that alone cannot explain baryogenesis. Okay? So we know that we need something beyond that. We do not know the origin of neutrino mass, does not come from standard model. There are some unexplained anomalies in data. Some stay for a long time, some go away, but there are still some anomalies that you should not entirely neglect, and they indicate to us that perhaps there is some standard model, something beyond standard model. Of course, these 3 things that are on top are definite indications that there is something missing that we need to understand. Okay? So therefore, physics beyond the standard model must exist. Okay? But then we have to figure out where to look for it, how to identify it, and how to quantify it. And that is all that our attempt is. No? Theorists and experimentalists, through their own means, try to find out different places to look for it, because sometimes you lose a ring and then you don't know where to find it. You have to go where the light is and look below the lamppost, so to say. So maybe we'll find something. Okay. Thank you.
I should apologize. I started taking mu plus p minus is from why didn't we do k log to mu plus p minus? I went and searched. It was actually measured and branching ratio is 10 to minus 9.
Okay. Okay, thanks.
1 billion k logs.
Okay. So k log is something which already decays after traveling a very long distance.
That's why it was very difficult to do, but it's okay with an experiment.
Thanks.
Yeah, thanks, sir. So any question, but question is already 1 and 2. Not...
Thank you, Professor, for your wonderful presentation. You talked about the neutrino flavors in standard model. That from proton-proton interactions, pions are produced, and from that pions, muons, and from muons, electron neutrino. I mean that the electron neutrino, muon neutrino, and tau neutrino are produced, but their ratio always remains same. That is in the proportion of 1:1:1. How is this possible, and how will it physically imply?
So I guess the question is, why are they produced in the same proportion?
Yes, sir.
But this is actually not true. So when pions decay, it is not true that muon and electron neutrinos come in the same ratio. In fact, in the pion decay, the fraction of electron neutrinos produced is extremely small, 10 to the minus 4 or so. So it actually has to do with actual calculations of these processes. We can talk about this later, okay, because this involves things that we did not discuss in this lecture. Okay. But there are very nice arguments by which you can actually figure out why is it that pions decay mostly to muons and for a very small fraction to electrons. interesting aspects of standard model. Yeah.
Hello, Professor. Thank you for your very nice lectures. Using the fact that you are speaking about very quickly about the physics beyond the standard model, could you please explain just a little as brief as well? Because we talked about the CP violation weak interactions. Yeah, can you please introduce us on strong CP violation on strong interactions?
CP strong interaction.
Yeah.
Okay.
I know that's very theoretical thing, is not so much into experimental, but I think is very.
Yeah. So let me just mention a few things. As far
Thank
as
you.
we know, CP violation is not there in strong interactions. Okay, and that's in some sense a puzzle. Okay, that's often what is called as the theta puzzle, because the contribution to strong interactions, we try to write down gauge theories where anything which is not forbidden should exist, right? So given that principle, the fact that we impose parity conservation in strong interactions seems like an extra imposition. There is this parameter called as theta parameter in QCD, which actually is what seems to violate CP. Now, this parameter has a few different contributions, but this parameter can be measured from the measurements of neutron dipole moment, electric dipole moment of neutron. Now, that dipole moment has very, very strong constraints on it, about 10 power minus 24 electron e centimeter or something like that, which basically tells you that this extra parameter that could show violation in CP, violation in parity of strong interactions, is 10 to the power minus 10 or smaller. Okay. Now, why this happens is a puzzle. It's called the strong CP problem. There are solutions which postulate particles called axions, but again, something that goes beyond this. These were standard model lectures. We can talk about that at leisure over lunch. I'll be here for lunch, if not for the lectures on all these days. We could discuss it over that.
Okay, thank you. Thanks, Amol. I hope this is they have a good platform from your lectures and which they will continue next 3 weeks. 2 weeks. And on the behalf of the school, I just want to give you a small momentum. Commemorate the school. This is the same thing. Not exactly the same thing. This is a slightly different kind of painting.
Wonderful.
Okay.
Thanks, Gabi.
Okay, and not like all other speakers, but okay. But he's also Sunday, but he is in TIFR. Next 2 weeks, anytime you can interact with him for any discussion. Yeah, Aman,
Yes.
I am right that they can come anytime to your.
Yeah. You can even come to my office. The office is A306. If you find me in my office, then I'm there to talk. But best time to find me perhaps is at the lunch table, because as I said, I will be here.
Okay,
Yeah.
okay, thank you. Okay, so let's start this third day's sessions and start with Professor Dighe's third lectures. Landscape of the standard model. Yeah.
It works now? Yes, it works. Maybe I move it slightly down. Okay, right?